Hello everyone. In this video, we discuss mathematical building blocks of machine learning, including data, calculus, linear algebra, mathematical optimization, and probability and statistics. And the goal is to show you how all these things work together to enable learning from data and making predictions. Before getting started, we should discuss why even we should use machine learning. Let's motivate this through a real-world application. Let's say you want to design a system for predicting bank loan default. And in this case, we have, let's say, only two features. So for each borrower or applicant, we have information about income and debt. The classical way to solve this problem is to write down a step-by-step instructions or rules. For example, you can have different income brackets, and then for each one, you define different ratios of debt to income, and they decide whether a borrower is going to default or not. As you can see, this is shown in this case where you have your features, including income and debt, and the rules that you have found, and now you use these to find these responses. And in this case, we can think of this as a simple binary case, yes or no. On the other hand, a machine learning approach is different in the sense that we do not want to explicitly write down instructions or rules. And instead, we take a data-driven approach. What this means is that we're going to look at some historical data, meaning that past borrowers with their information about income and debt, and whether they defaulted or not. And in this case, the inputs to this machine learning system is technically features and their corresponding responses. So features are again income and debt, and responses here are simply yes or no. And our goal is that hopefully this machine learning system that we have here is going to automatically extract some hidden rules or structures that can enable making predictions so that if in the future we have an applicant with certain income and debt, now we can use those extracted rules and make predictions to figure out whether it is likely that that applicant will default or not. If you want to put this in a more mathematical context, you can see that we can think of this as a two-dimensional problem where we have these x and y axes with debt and income values. And each data point here is one past borrower, and the labels here are color-coded, right? So we have yes and no. And in this case that we have a two-dimensional example, you can see that it is very easy to find these rules that we talk about, right? So it's possibly a line that goes through the two that goes between the two classes and separate them. So if you want to summarize what we just talked about, a machine learning system is trained rather than being explicitly programmed. And there are several benefits or advantages. And one is that in many cases, it's easier to develop and maintain because you're not hard coding these rules or structures. And if you have enough or adequate amounts of data, then possibly it is more accurate than traditional or classical approaches. But there are also some challenges too. And the first one is that you need both features and responses. And this is what we refer to as label data. So when we talk about label data in machine learning, we mean that we have the features that are inputs, and then we have responses that are kind of like the outputs of our machine learning system or what we ideally want to predict. And there are also other considerations too, because in many cases, these rules that are automatically extracted by machine learning systems, They need to be also trusted, meaning that we need to make sure that they're interpretable. They are also not biased towards certain groups. And so there are a lot of also interesting challenges and open questions when applying machine learning systems. And as we just mentioned, in machine learning, data labeling involves assigning labels to raw data. So this can be tabular data that we just discussed. It can be images, it can be text files, it can be videos. For example, you may have like different like ads on TV, and you want to predict whether they are scary or not, or appropriate or not. So these are all different ways of labeling raw data. And something important to mention is that machine learning really moves beyond the confines of traditional statistical techniques and optimization algorithms in several aspects. So one thing is that in machine learning, because the goal is to solve real-world problems, complex real-world problems, we usually deal with really nonlinear and complex structures that they need to be extracted. And this is important because in many traditional domains, we focus on simplified models, in particular linear models. But in machine learning, the ultimate goal is to be able to find really complex and nonlinear models. And then the other thing in machine learning is that we really care about adaptability and generalization. We live in a dynamic world. And so, although in this course and some other like textbooks, we mainly focus on like static data sets. In real world, you have unknown and changing environments, so you want to make sure that machine learning methods can adapt and also can generalize. So what this means is that obviously when we have some historical data and we already know the answer to those data points, so that's something that is known. So there's really, training is a very important part of machine learning. But if we do well on the training data, then that's not really helpful. Like the goal is to always be able to perform well on new or unseen data points. And that's what is usually referred to as generalization. Also, you can think of that as extrapolation. The other thing is about the scalability to big data. So in many cases, we have large amounts of data. For example, there is a very popular data set in machine learning known as ImageNet, which I believe we have about like 14, 15 million images. And so you can imagine training a machine learning model using such a huge data set is definitely challenging. And these are important aspects of modern machine learning. And the last thing that we want to mention here is that in modern machine learning, the goal is to be able to provide as many features as we can collect, and we hope that the machine learning system is able to identify important features and also find a meaningful representation of data. What I mean by that is that, for example, if we go to this example of what we call it as the MNIST data set, which is the hello world of machine learning. So each image here is one digit, like these small images that you see here. And these are 28 by 28 pixel images. So this means that if we vectorize these images or flatten them, there are going to be about exactly 784 elements or dimensions. So if you want to think about this as a mathematical problem, each data point, each of these images is one point in a 784 dimensional space. And obviously that's a very complicated problem to for example, be able to classify these digits or do other machine learning tasks. Therefore, one of the main objectives of modern machine learning is that can we get these really high dimensional data points and be able to transform them or map them to a very small or low dimensional space where we can easily find some interesting rules or structures. So here you can see that we have used some form of neural networks, even though I've not officially defined them yet. And these each circle or point here is one of these images in a two-dimensional space. And we have color coded them based on their like the digit that they represent. We have 10 digits, right? So 0 through 9. And you can see that this low dimensional representation, even though it's very aggressive in a sense that we went from 784 dimensional to two-dimensional, still we can preserve a lot of structure in a sense that a lot of these, for example, digit 1 data points are clustered together. I mean, obviously there are some of them a little bit farther away, but this is a very complex problem. Still, we are doing very well. You can see that, for example, like digit 9, or similarly like digit 7. So that's like really like the impressive part of modern machine learning. So I wanted to kind of like show you the difference between classical and more modern machine learning, right? Because in classical machine learning, statistical learning, we usually work on really low dimensional problems, like what we had with income and debt. And there are like methods such as logistic regression. We're going to talk about this in a few weeks that we can use to classify these data points. But this is not enough really in many modern problems. And we really have to figure out problems with high dimensional data points. And by high dimensional, I mean thousands or millions of features. For example, you may have some gene expression data. Obviously, these types of data sets are really high dimensional. And also the other part is that we have high risk, high reward investments, right? So once you start to incorporate machine learning in autonomous driving, in medical diagnosis, um, like it is very important to make accurate and reliable decisions or predictions. And that's something that, part of modern machine learning. So now let's dive a little bit deeper into the mathematical aspects of machine learning. So one thing that we're going to use throughout the semester, almost like for every lecture that we have, is this general diagram for machine learning models. So you can think of this is that we always start with some features, or right now, because I think of a machine learning system as having some inputs and outputs, I call them just inputs, right? So this can be, for example, income and debt. And then what we do, we start transforming these inputs that we have. This can be only one transformation, or it can be multiple transformation. That's exactly the difference between classical versus modern neural networks and deep learning models, that in more modern models, you have multi-layer representations because you have more complex models. And then we find some predicted outputs. For example, that can be the answer to that bank loan default problem, yes or no. And then for the historical data that we have, or the training data that we have, we also know the outputs or responses. So the nice thing is that now we can actually supervise this model, meaning that we can see how like the level of agreement between predicted and expected outputs. And this is done through loss or cost function, which is very important. We're going to focus a lot in this course about loss and cost function. And then the next step is to use an optimizer to figure out how to tweak these weights or these parameters that they determine how we transform the data to make them better so that predicted outputs match better with expected outputs, right? So you can see that it's this closed loop system where we can start from any kind of like, bad solution or random solution and try to improve that solution iteratively. So there are different ways of categorizing machine learning algorithms. One is based on the data supervision or data labeling. So if the problem that the algorithm that you have is trained on data sets that all data points in them are labeled, meaning that they come with features and responses or inputs and outputs, this is called supervised learning. And it's one of the most important parts of machine learning. That's what we cover in this course. But then there is also the exact side of this problem, where we have these inputs or features, but we do not have any responses or outputs. This is something that you can see a lot these days in generative AI, right? So in generative AI, we have some raw images. You do not even have probably like labels for them. They can be, different images of cats, dogs, and, other animals. And then the goal is to generate new ones that they kind of look like real ones, right? So in this case, we don't really need any more labels because the goal is not to predict whether, you have a cat or dog in an image, but the goal is to create new realistic images. So that's something really interesting for certain applications, but it's beyond the scope of this course, and for the most of this course, we focus on supervised learning. However, something that is very important is that the overall actually way of training unsupervised learning methods, it's very similar. And that is exactly why here I'm using the term expected outputs rather than true outputs. Because in the case of supervised learning, you do have the true responses or true outputs that come with your historical data. But if you have like unsupervised learning, you can think of that as you want to, for example, predict outputs, and you don't know exactly what those outputs are because your data is unsupervised, but you can have expected outputs, right? So that's why I use specifically the term here, expected, rather than true outputs. So overall, what we learned in this course, obviously, will help you a lot to understand unsupervised learning methods, but something we do not directly cover. And then have something in the middle, which we call this semi-supervised learning. And this is a combination of supervised and unsupervised learning. So this means that usually you have a small amount of labeled data, and then you have a lot of unlabeled data. So one of the applications of this, why this can be important, is that let's say you want to develop a machine learning system for a manufacturing problem to predict some mechanical properties of items that you are printing. This is a 3D printing problem, one of the projects I work on. And you can see that in this case, if you want to collect both inputs and outputs, meaning that you have to run these experiments, you have to use a printer, materials, like labor costs, etc. So usually you're limited in terms of how many input-output pairs you have. So in this case, you can assume that, okay, I have like 100 of these input-output pairs, but also I have a lot of inputs that I can provide to my 3D printing machine, but I do not really have resources to perform all those experiments and measure these outputs. So in this case, the question is whether having this extra unsupervised data or unlabeled data will help us to develop better machine learning models for making predictions. So it's a very interesting and active area of research where you have limited budget for labeling data. Another way to um, classify machine learning algorithms is based on model complexity. We do have linear models, which they assume a linear relationship between the input features and the outputs or responses, right? So we can assume that, for example, in this case of mechanical properties, that each property is a linear combination of inputs. And this is a very simple problem known as linear regression, but obviously not able to capture complexities of many real-world problems. Therefore, we have another class of nonlinear models that they can capture more complex relationships. But something I want to emphasize here is that when we talk nonlinear models, this does not mean that we only have neural networks or deep learning models. There are actually other nonlinear models too, such as tree-based models and so on. Then the third category, which is the subcategory of nonlinear models, is what is neural networks and deep learning models. And the main distinction between this category and linear models is the fact that we can have many layers or many the levels of transformation. So that's exactly what we had here. Usually in linear models, we have one transformation. In deep learning models, we have a multi-layer transformation or representation. And therefore, in this course, we actually start with more simplified cases, and then we show the connections, how you can extend these to develop deep learning models. They also have another way of categorizing machine learning algorithms based on the output that we get from them. So in most cases, especially what we cover in this course, we focus on deterministic models, meaning that if, let's say, you want to find mechanical properties of an item, you get a single number for that property that you're looking for. So you don't account for any kind of predictive uncertainty. And although these types of algorithms are typically straightforward to implement, the problem is that we don't get any notion of uncertainty or how we can trust these predictions. Therefore, there is a lot of effort in terms of being able to quantify uncertainties. One thing that we do cover in this course is this idea of conformal prediction. And this is really nice because it requires minimal distributional assumptions about your data, and also they are relatively fast. And you can provide any deterministic machine learning model, feed them into this conformal inference framework, and you can get prediction intervals or sets. So this is something very helpful, and we're going to talk about this in this course, one of the very last lectures that we have. But also I want to bring this to your attention that there is another line of machine learning algorithms, which we call these Bayesian models. So the main difference here is that for Bayesian models, we use Bayesian principles to handle uncertainty. So meaning that we have to make assumptions about the prior distribution, then we find the likelihood of the data being generated with some parameters, and this allows us to find the posterior distribution. So that's exactly the main idea behind Bayesian modeling. And this is something that we do not directly cover in this course, but we have a few exercises throughout the semester to show you how Bayesian modeling actually can be used. So now we can go a little bit more talking about mathematical building blocks of machine learning. And the first thing that we have to do, we start with the way that we represent data. So remember, we have features or inputs, responses or outputs. And therefore, in the case of supervised learning, we can show our data set using a set of input-output pairs. In programming, we call this a tuple. But in the case of mathematical language, we usually call this input-output pair. And then we have these curly brackets for the sets. And then we have here n goes from 1 to uppercase n. So this small n is used for indexing, is the subscript, and the uppercase n is the number of data points that we have. Therefore, each feature that we have, or each input, in this case, is a two-dimensional vector, right? We have information about income value and debt. And that's why you see that we have to use a lot of linear algebra to solve machine learning problems. And in the simplified case that we just talked about, the output or the response is a small set that contains yes or no. And since we like to work with numbers when we're doing machine learning, because that's how we can work with these algorithms, they work with numbers, then we can represent this using 0 and 1. 0 means no, 1 usually means yes. But in a more general case, especially when we have a classification problem, you may have C classes, right, and 2 classes, right? So in this case, we represent these classes 1 to C. For example, for that image data set, we have 10 digits, 10 classes. We can represent them 1, 2 through 10. Or since digits start from 0, we can also say 0 through 9. Remember, in this case, these like numbers that we have here, they are usually just some labels and they do not have any quantitative value. So you can really, if you want, use any, C distinct numbers, and that's what we need. However, when we get to regression problems, in those cases, the goal is to predict a continuous output, right? So that's the main distinction between classification and regression. And in the simplest case, you have one output or quantity of interest, and that can be any real valued number. But in a more general setting, you may have multiple outputs. For example, in a manufacturing problem, usually you look for multiple mechanical properties and not just a single one. And therefore, here we have RO, where O is greater than or equal to 2. For now, let's just focus on the simple case of binary outputs. But throughout the semester, we're going to focus on all of these types of outputs. The first thing that you want to do when you want to train a machine learning system is to do model fitting. So what does this mean? So the way that model fitting works, if you look back at what we have here, you get some predicted outputs, you have some expected outputs, and you need to have a loss or cost function that accepts these two and compare them, right? So here is mathematical representation of what we have. We have this function L that has two input arguments. One is the true response or true output. So this comes from our historical data. On the other hand, we have our input features that we pass through the multi-layer representation. And this theta here represents the weights or the parameters that we have, right? So this is here xn, this is theta, and the output is f of xn and theta because this is a function of both. And this is our expected response or prediction. And then what we do, we find the average loss on the training data that we have. Let's start with looking at some examples of loss function. So in the case of binary classification, where y is either 0 or 1, there are two possible scenarios. One choice of loss function is indicator function. This is what this I is of y not equal to y hat. So what does indicator function do? If this statement that we have here is true, then we get 1, and if it's false, we get 0. So if it's true, means that y is not equal to y hat. So it means that the true and predicted outputs are not the same. And if this is false, then means that y and y hat are actually equal. So that's this if condition that we have here. And in this case, we get 0. And this makes sense, right? So basically what we're saying is that if you make a correct prediction, there is no penalty to pay. That's what loss function does, is trying to find a penalty so that your model performs well. So if we make a correct prediction, we shouldn't pay any penalties. But if we make a wrong prediction, then there is one unit, you can think of this as one unit of penalty, right? So this is what is called as the 0-1 loss, right? It only takes two values. And why is this very popular? Because then what we have here, the summation over all the data points, remember this small n is for indexing, is the number of misclassifications. And then if you divide this by the total number of samples that you have, you find misclassification rate. And obviously the goal of a machine learning system in this binary classification is to minimize the misclassification rate. And this is what we call it as the empirical risk minimization, meaning that you first form the empirical risk, which is the average loss on the training data. So this loss can be the 0-1 loss or other loss functions that we're gonna cover in this course. And then your goal is to find the settings of this data or weights or parameters that minimize this objective function that we have, this average loss. Something I want to emphasize here is this notation that we use, this f of x and semicolon theta. So why we are kind of like distinguishing between these two. And this goes back again to that diagram that we have. So remember, xn represents input features, income and debt. And then you have these parameters theta that you're going to use to transform your input features. And the difference here is that the input features like this income and debt values are actually given to. That's based on your historical data and the past borrowers where they reported their income and debt values. And therefore, there is really nothing to optimize for xn. That's given to us. The only thing that we really want to optimize here is that how we should process or transform the data. So therefore, you can say that, well, these predictions that we have is a function of both of xn and theta, but xn is fixed and theta is what we call it, especially in the deep learning language, as trainable. So in this case, that's why I use this notation to show that what we really want to optimize here is this theta. And xn's and yn's are coming from your data set, and this is fixed and given to. So there's really nothing to change here or optimize. Therefore, that's something to keep in mind. And the nice thing is that once you learn the optimal value of theta, and by optimal, we mean that values of theta that minimize this average loss, now you can have new inputs like a borrower or an applicant with new income and debt values. And you know the optimal value of theta. And so you fully know this function and you're able to make predictions for this new or test data point. And the nice thing is that now, if you assume that somehow you have the label or response for your new input, you can now put this back or plug in this back into your loss function and see how good that prediction is. So that kind of explains the entire process that we have here, where we start with these xn's for inputs. You find predictions, you do this comparison, and then you try to find the optimal values of theta. What we just discussed obviously does not work for regression problems, because in regression problems, y and y hat are real valued. And in this case, you cannot simply just see if y is exactly equal to y hat or not, right? Because there are real valued numbers. So the most common way here to measure the distance or difference between the two is the quadratic loss function. So you subtract them, raise them to the power of 2. And this is what is known as the mean squared error, or MSE, which is a very popular way of measuring the quality of regression problems. And just to discuss about this data transformation, if you have, like, let's say, a simple linear regression problem, what you do is for each input feature that you have, for example, this might be income, this might be debt, you assume a weight or a parameter, and then you find a weighted sum. That's what we call it as a linear combination. And so the goal is really to find this W1, W0, WD. And finally, you will see that the way that we actually, the interesting part about this course is that we show that we can move from simple models, such as linear regression, to more complex ones, such as deep learning, by considering that multi-layer representation that we have. So what this means is that, remember that we have here these like features that we talk about, these xn's. I call these original features. Now you can send these through multiple data transformations. And these data transformations, they're parameterized by, let's say, V, where V is a set of parameters. We're gonna very soon see that like this V can actually have millions or billions of parameters in current state of machine learning and deep learning. And what happens is that this will give you what we call as hidden features. So it's a function of xn parameterized by V. And in many of the even like the most recent models, you can see that in the final stage, we are still using linear regression. So that's exactly what we had there, the inner or dot product between these hidden features and some, weights or parameters. And the fact that matters here is that the main contribution in these models is to find these hidden features or representation. So there's this really nice connection between simple or linear models and more complex neural networks. So this is a good time to also talk about generalization. So we talk about this for machine learning models. The goal is to make sure that they perform well on new or unseen data. And the reality is that in many cases, machine learning models tend to perform worse on data points that they have not seen before. And so this is something that always a concern and something we have to pay attention to. So therefore, the question is, how can we evaluate machine learning models and select the best one? So the simplest thing you can do, given the data that you have, remember we have that data set that we showed using D, is to use train test split. So this means that you divide that set into two parts, one training and one test sets, and they should be exclusive, so no common elements. And you use the training data or D-train to form your empirical loss or this empirical risk. And then we perform empirical risk minimization to find the optimal values of theta. And when you do that, the next step is to now test the performance of your model using this unseen data. So this allows you to be able to actually find these loss function values for the test data points because you actually know the responses or outputs for those data points. And this is something important because in many cases, we do not have access to more data points to generate their outputs and see how we really perform on something that we have never collected before. We just have a little bit of historical data that we have to use or a given historical data. So therefore, the only thing that we can really do is to divide this into two sets and make sure that we do not use this test set anytime during training or fitting so that this is really new to the model in the evaluation stage. And although this works for simple cases, one issue is that in many more like modern methods, we have a lot of degrees of freedom, or what we call it as hyperparameters, meaning that parameters that they have to be set by the users. For example, how many layers of transformation we want. So these are things that we usually cannot learn, and we should provide that input as sort of like guidance for our machine learning model. And therefore, in these cases, if we do this multiple times on the training set and then use the test set multiple times to see, well, which, for example, number of like levels of transformations is the best one, then we get to this problem that we have used this test set many times. And therefore, really, it's not anymore a way of measuring generalization error. So therefore, a more common approach and appropriate way to evaluate machine learning models is using train development or validation and test a split. So in this case, you divide your data into three portions. You use the training set for training or model fitting, estimating the parameters, and then you use your dev or validation set to find those hyperparameters. For example, again, this really becomes important for neural networks and deep learning, where you can have like one layer of transformation or you can have like 100 layers of transformation, and that's something that you have to provide. And once you do this multiple times and you make a decision about, well, which model is my final best model that I want to use, then you get to use this test set only once. So that's something to consider, that we can repeat this first stage multiple times. Once you select the final model, this is called model selection 2. Now you use your test set only once and you evaluate the model. Although I mentioned earlier that we are not going to work with Bayesian modeling very much in this course, but we will take advantage of maximum likelihood estimation. So why we should use maximum likelihood estimation? Because if you think about it, once we are having this diagram here, we have these weights or parameters that they're unknown. So in some sense, supervised learning is really a parameter estimation problem from the statistical standpoint. So, and one of the most important ways of estimating parameters in statistics is using maximum likelihood estimation. So the idea is that you form something called the likelihood functions, which measures the probability of observing the data for different parameter values. So you condition your data on these parameters, and then you aim to find the thetas that maximize this likelihood function. That's why it's called maximum likelihood estimation. And one of the most important assumptions here is that we assume that all the observations or data points that we have, they are IID, independent and identically distributed. And with this assumption, the probability of observing your data, given some parameters theta, is the product of the individual probabilities of yn given xn and theta. And therefore, the problem is to find theta, values of theta that maximize this likelihood function. One thing that we have to consider is that maximizing this function, the likelihood function, is difficult because it's a product of these probabilities. But from probability calculus, you know that there is a very nice trick to transform this into some of these probabilities, and that's using the logarithmic function. So if you take the log of these, log of products is the sum of logs. And so what we really work with is the log likelihood function, which we represent as the LL function. And then the other thing that we have to consider for machine learning problems is that we usually like to think about loss function or cost function as a function that measures disagreement and something that we want to minimize. And so the next step is to convert this maximization problem that we have in MLE to a minimization problem. And that's also very simple. You just need to multiply this by -1, and we get something that is called negative log likelihood function, or NLL. So we're going to see in this course that all the loss functions that we are using, and they're very popular in machine learning and deep learning, they can be derived from this negative log likelihood function, right? So the idea is that you want to minimize this this objective function here, which is the sum of this negative. We can bring this negative sign inside this summation, negative log of individual probabilities for each observation or each output given inputs and this parameter theta. To show you how this works as a warm-up example, let's look at Bernoulli distribution, right? So this is something that also helps us later to figure out how we can drive loss function for classification problems, because remember the binary classification that we have right now, the output is either 0 or 1, and that's actually a Bernoulli distribution, right? So what is the probability density function with parameter theta for a Bernoulli? So if y equals 1, that's theta, and y equals 0 is 1 minus theta. So since the sum of probabilities must equal to 1, so when you have 1, we should call here theta, the other one should be 1 minus theta, which means that we only have like one parameter or degree of freedom. And we can actually show this because usually in machine learning, we don't like functions that they have multiple parts. That's difficult to work with. We can summarize this in one equation, and that's this theta raised to the power of this I, which is the indicator function of y equals 1 minus theta I, y equals 0. So remember, if y equals 1, then this indicator function here is 1 and this one is 0. So this means that we get theta. And then we have the other side. If y equals actually 0, then this is 1, and 1 minus theta raised to the power of 1 is 1 minus theta. And then we get theta raised to the power of 0, which is 1. So with this in mind, what we can do, we can form the negative log likelihood function, and this is a function of theta because that's what we want to estimate here, and which is unknown given some observations. And that's the negative sum of this log of observations given thetas. Something that you can do is that if you take the log of this, right, because you can think of this as a times b, and log of a times b is log of a plus log of b. You can simplify this, and I think we have the full derivation here. So if you take the log of this, then you get the log of the first term, and then that would be this indicator function log of theta plus you get this I indicator function of yn equals 0 log of 1 minus theta. So that's your logarithmic function that you have here. And you can see like how easier it is to work with this because now you don't have to deal with these exponents here. And that's why really the idea behind working with the log of the likelihood function. So with this in mind, we get to this line. And the nice thing is that this log of theta here does not have any index n. So this means that now you can just factor this out, and we only have this negative sum of this indicator function yn equals 1 times log of theta. So this is now outside this summation, plus the same thing log of 1 minus theta. And again, if you think about the way that the indicator function works, so this first summation measures the number of cases that we have seen once. So that's the N1, the number of ones that we have seen. If we have done, let's say, 100 or I don't know, like 1,000 trials, and we are seeing these values of this Bernoulli random variable. And the second summation here is this N0. So that's our negative log likelihood function, which is negative N1 log of theta plus N0 log of 1 minus theta. And now if we go back to calculus, so you can see that we are going through calculus, probability, and statistics. That's the really nice part of machine learning. Now, if you want to find the solution of this problem, the very first thing that we need to do based on the first derivative test is to take the derivative of this with respect to theta. And this is straightforward because you have this log of theta, and the derivative of that with respect to theta is 1 over theta. You can also, if you want, use chain rule and simplify this too. And if you set this equal to 0, you will see that the estimate that we have for theta hat, and that's why I call it theta hat of MLE, because it's derived from the maximum likelihood estimation, is the number of cases that you have seen once divided by the total number of samples, which makes sense. If you have let's say, a Bernoulli random variable, you have 100 different trials, and 60 times you see once, then that parameter theta that we have is 60 over 100 is 0.6. It's a very easy to understand, like estimation here. We're going to talk about programming aspects of this course in the next 2 lectures, but I thought that it is really nice to include a preview here to see how everything works together. Since we are working with some numbers here, we import numpy as np, so that stands for numerical Python. For visualization purposes, we are going to work with matplotlib, which import this, and we call this plt. Here, I'm just gonna kind of like just go through each line to explain to you what each line does, but we're gonna go more into details later on. So here we want to change the font size and the figure size, The most important thing is that we want to make sure that we have defined this N0 and N1 that we have here. So I assume that N0 is 40, N1 is 60, right? So we have 100 trials and 60 of them are ones, 40 of them are zeros. And then you have to define this negative log likelihood function, which is negative N1 log of theta. So that's like one of the reasons we're using NP, because this logarithmic function has been implemented there. So that's like really nice. So we have this np.log of theta plus n0 np.log of 1 minus theta. This is the really nice thing about Python. It's very easy to read the code and make sure that that is consistent with the math that we have. And the next thing, if I want to plot this function to visually find the minimum, you can also create some values of theta from 0.001 to 0.999. So probability is technically from 0 to 1, but I don't want to get into numerical problems with the log of 0, or similarly here, if I plug in here 1, I get again log of 1 minus 1, 0. So that's why I'm avoiding those two sort of like extreme points, and we're going to create 1,000 equally spaced points from 0.001 to 0.999. And we're going to plot these inputs and then outputs. So these are all the x values, all the y values. And also in NumPy, there are ways to find that at which location you encounter the minimum and what actually the minimum value is. So that's here you have the argmin, which tells us where the minimum happens, and actually the minimum value. So that's the difference between min and argmin. We can also use a good practice to label these axes to make sure that we understand what this, prefigure that is going to be printed soon or displayed soon means. And if I run this cell, you can do this using Shift Enter, you can see this negative log likelihood function. And this is exactly what is, what we expected, that the optimal value of theta should be 0.6. And again, I want to emphasize here that here we work with argmin, because what really matters here is that for which value of theta this negative log likelihood reaches its minimum value. So the minimum value here doesn't matter as much for the purposes of, what we wanted to do. It might be 80, 90, that doesn't really matter. The thing that really matters is that what is the optimal value of this input theta that leads to the minimum value of this function. And we can easily see this. And this is a really nice thing about this course, that you can really get a good sense of, the problems you work on. You can visualize a lot of them. You can also confirm that the math is correct. So there are a lot of ways that you can use programming to solidify your mathematical understanding. So in this case, obviously we use more like a visualization perspective, but also we can use more concrete approaches to solve this problem. So there is a library in Python, which is called SciPy. And inside that, there is a module called optimize. And so you can use that to optimize functions. And one of them is to minimize a function. And in this case, the way that this works, this minimize function accepts three inputs. First, the function to be minimized. Here is the negative log likelihood function. Also, the initial guess, right? Because a lot of solvers, the way that they work, they need an initial or random guess, and then they try to make that, better and until to the point to get to the minimum value. And also the bounds for this theta. So this really helps to restrict the search space to find theta. So you can see that how, straightforward it is to apply this. So from scipy.optimize, from this module, you import minimize. Then you have your initial guess. Let's say we assume that this is a fair process, so it's 50-50 the chance of getting zeros or ones. We provide our bounds, and then you call this function minimize with these three input arguments. And if you run this, you can see here that you get some information about convergence and other things. And you can see that the value that minimizes this function is 0.6. And if you really want to show this information or print that, you can say result.x, right? So x here doesn't mean this is the x value that we have. It's basically what input minimizes this function that we provided as the first argument. And you can see that this is exactly what we expect. So in this Bernoulli distribution case, which we use because of its simplicity and also being able to get a little bit of warm-up example, we had a case we had only one optimization variable. But the fact is that in many modern machine learning methods and deep learning methods, we have a multitude of parameters that they need to be fine-tuned. And one example of this is that very recently, in July of 2024, Meta released or Facebook released their large language models, which are very hot topics these days, called Llama. And this model has 405 billion parameters. So you can see the difference, right? Right now we try to optimize one parameter, but this model has 405 billion parameters. And you can click on this link and get some more information. But what I really like to show you here is that still the principles, and this is the diagram and the architecture I got from this blog from Meta, and is that it still is the same exact principles that we just discussed. So we have some inputs here. We have like text. When you're working with text data, you cannot just give your machine learning method model the raw input. You usually have to do what we call it as tokenize this, which means that you divide your text into words or characters or subwords is always called as tokens. And so this way you can actually give some numbers to your machine learning model, the number of cases or the number of times you have seen like word hello or other words or tokens that you're interested in. So that's why this is the first step, the pre-processing. But after this, it is really the same principles that we just talked about. We have multiple layers of transforming the data until you get your output. And in this case, especially when you work with text data, your output is like the next token or the next word that you have, right? Because you want to complete a sentence. And you can see that now this is going to be now the input, and it's going to be used to predict the next word. And for example, in this case, you can see that they're using feed-forward neural networks, and that's like one of the most basic types of neural networks that we cover in this course. So this is just to show you like some of the differences between what we cover here and some really state-of-art machine learning systems. And at the same time, I want to show you that a lot of things that we cover in this course, they're actually very much applicable. And then for the further reading, you can read the first chapter of Probabilistic Machine Learning: An Introduction. This is a textbook that is, free to download the PDF. So it's an open educational resources. So it's gonna be really, interesting to read that chapter and kind of get a little bit more formal introduction to machine learning. And since we talk a lot about loss functions and cost functions, I found this article, which is really, I think, interesting because it talks about the importance of the choice of loss function and how, there are usually like multiple loss functions for a problem. So that's something that I encourage you to read. I hope you found this video helpful, and thank you for watching.